Hello everyone, and welcome back to the session 4 of NPTEL online course Drug Delivery Principles and Application. Before moving on towards this week assignment, are you guys getting the links of the previous sessions, the YouTube links for the first, second, and the third week? Has anybody gotten it? Hello, am I audible?
Yeah, ma'am. I'm not getting links from NPTEL, ma'am, regarding the YouTube.
Okay. So I'm going to post the three links here for the previous three sessions in the chat box. You can copy it from there.
Okay, thank you, ma'am.
Yeah, I've posted the link for all the three sessions. You guys can copy it because the links will not be available once I end this call. So we can start with the next this week's session. Let me just share my screen. Can you all see the screen in slideshow mode? One of you can unmute your mic and let me know. Anybody? Is this visible?
Yeah, ma'am, we can able to see.
Okay, sure. So have you guys gone through the week 4 lectures? Before we discuss the assignment, I need to know if you have gone through the lecture so that we can go over it in a bit more detail.
Yeah, ma'am.
Okay. So I'll just go over the quick recap of this week lectures. So since it's been a month that you are learning this course, we are learning about drug delivery, and we have seen pharmacokinetics in the first few lectures, and we are looking at different drug delivery techniques for a controlled and sustained release of the drug in the body. And in this, we have seen certain techniques like polymer drug conjugate and reservoir systems, where we have seen systems which do not bioerode, they just stay in your body as it is, but the drug will slowly diffuse from these systems and will be available for its bioactivity. On the other hand, we have seen bioerodible matrices, where your polymer, the matrix which is made up of polymer itself is going to start degrading after a while at a certain rate. So your drug will be diffusing as well as it will release out of that polymer system as and when it degrades. In this system, we have also seen hydrogens, which are polymers which are capable of absorbing a lot of amount of water, as a result of which they swell. And after they swell, the drug comes out from the pores, which are formed due to the swelling of these polymers. Now, if we look at all of these techniques one by one, we come to know that in all of these methods, we at least have to perform one surgery on the patient, where we have to uh, implant these matrix systems inside the body. For example, if you have a reservoir system, if you have a sphere made up of polymer and your drug is inside that polymer, you have to implant it into the patient body. And after when the treatment is over, when the patient is cured, you have to again retrieve that. You can't leave an implant inside the body for a long time, so you have to perform another surgery to remove that. So this is in case of non-bioerodible systems. In case of systems which bioerode, you have to perform at least one surgery to implant it, and as and when it degrades, you don't need another surgery to remove it. Now there is another class of drug delivery systems where we don't need implantation of these systems. These are known as micro and nanoparticles. So that is the theme for week 4 lectures. If you have seen that all of these lectures are based on the micro and nanoparticles. So these particles are very much advantageous in the case that they can be injected into the body. As a result, you don't need to perform any surgery to implant them. since these are of a micrometer and nanometer dimension, they can easily be taken up in a syringe, just like you must have seen people injecting insulin and so on. So these small metric systems can be taken into a syringe and they can be injected as and wherever you want in the body, in the system. So because they can be injected, you don't need to perform surgery, so they are more patient compliant if you compare it with the other systems which we have already seen. And what all things can be put into this micro and nanoparticles is you can encapsulate small drug molecules, you can encapsulate nucleic acids, you can encapsulate peptides, enzymes, depending upon what treatment you're giving for a certain patient. So these can be encapsulated. If you go further in the lectures, we have discussed some definitions related to these systems, such as polydispersity of these particles, then loading level, what is mean by loading level, what is encapsulation efficiency. You need to know these terms in order to understand these systems in a much better way. Then in the next lectures, we have seen several particle synthesis methods, which consist of single emulsion, double emulsion, solvent removal, etc. We'll be looking at double emulsion in some detail because that is one of the questions in this assignment. And next, towards the end of this week, something known as liposomes is also discussed. This is also one of the methods to deliver your drug efficiently into the body. So, what are liposomes? Liposomes are lipid bilayers, bilayer particles, which in which you can encapsulate your drug. Now, since these lipid bilayers are made up of the same material like your cells, because you must be knowing your cells also have a lipid bilayer, and the liposomes are also made up of lipid bilayer, they are much more biocompatible, meaning they will not elicit an immune response to such an extent like we have seen in the other cases. Also, the end lecture, I think it consists of certain drug delivery parameters, like things you need to keep in mind when you're designing your particles, such as size and shape of the particles, what all things matter. So we have seen elasticity also plays an important role, uh, and charge also plays an important role. We'll discuss some of these concepts in the questions we have for this week. Do you guys have any doubt in the session, in the lectures you have seen? If not, we can move towards the assignment. Shall we? Anybody has any doubt before we move on towards the assignments?
No, ma'am.
Yeah, so okay, thank you. So in this week, we are going to discuss the fourth assignment from the previous course. So let's move on towards the questions. So I hope you can see the questions. The first question is, what is proton sponge effect? And we have to select two correct options. So I'll read out the options. Particles carry secondary or tertiary amines, which helps in escaping endosomal and lysosomal vesicles inside the cells. It is a phenomenon which leads to osmotic swelling and bursting of vesicles. Particles act as sponges for electrons. The phenomenon where particles carrying positively charged moieties neutralize free radical moieties in an extracellular environment. The phenomenon of gaining positive charge during endosomal transport. A sponge soaks up all protons in the vicinity, and the phenomenon of gaining negative charge during endosomal transport. So you guys have to select two correct options for this question. So let me know if anybody knows the answer, if you guys have gone through the lectures. Anybody wants to volunteer? If not, we'll discuss the question in a bit detail. Anyone wants to volunteer? You can just unmute your mic and start speaking. I can't see if you raise your hands or chat in the chat box.
Option 1 and 2, ma'am.
Option 1 and 2. Okay, we have one answer. Thanks for answering. Anybody else?
Option 1 and 2, ma'am.
Okay, thanks for answering. Does anybody have a different answer apart from 1 and 2? Okay, let's move on towards the answer then. Yes, both of you are correct. The correct option is option 1 and 2. Let's look at what proton sponge effect essentially is. So proton sponge effect plays an important role when you want to deliver your drug inside the cell. For example, let's consider this as a cell, the schematic. Okay, so this is your cell membrane and you want to deliver your particles inside the cell. Now what happens is if you deliver your particles in the vicinity of this cell, it's going to take inside this particle. For example, let's suppose this is your micro or nanoparticle and you have your drug encapsulated inside this and you want to deliver this particle inside. Now the cell is going to take up this particle by a process known as endocytosis. It will just engulf this particle and it will go to a compartment known as endosome. Now this endosome can in future few steps can develop into a lysosome, which has a very lower pH. So lysosome pH can range from 2 to 4, which is highly acidic in nature. So the job of lysosome is to digest up anything, any foreign material it sees, and it will just digest, chop it up, and that's it. Your drug is lost. So this is not what we want. This is not why we designed the particle. We want the particles, your drug to be in the cytoplasm. So to avoid this endosomal and lysosomal chopping up of our particle, we make use of proton sponge effect. Now what is proton sponge effect? Let's read through this. So as I said, particles are uptaken through endocytosis by the process. So these particles will get localized in endosomes and lysosomes where the environment is very harsh, very acidic in nature. Now to help these particles, we have something known as proton sponge effect. So what happens in this is we can design our particles to carry certain secondary or tertiary amines. I hope you guys know what are secondary and tertiary amines. These are, so everyone knows ammonia, right? Ammonia is NH3. If you replace the hydrogen atoms with your carbon chains, we get secondary and tertiary amines. So if your particle has this secondary or tertiary amine group, what happens is in this acidic environment, they're going to take up all the H plus ions which are present in this lysosome. Because at acidic pH, they'll be negatively charged. So they'll just gobble up all your H plus ions since they are amines. So now what happens? There is no free H plus ions in this lysosome. Now lysosome wants to maintain its pH. So if all your H plus ions are getting sequestered by these particles, there are no free H plus ions. So what will happen is these channels will open up, the ion channels, H plus if you see here, and H plus will be pumped inside the lysosome to maintain its pH, acidic pH. Now this process keeps on continuing. If you pump in more H plus, your particles are again going to take up more H plus because you have the secondary and tertiary amines. Now so more and more number of H plus ions will be pumped. Now to balance those out, the extra H plus ions, chloride ions will also be pumped because chloride ions are negatively charged. They'll neutralize the H plus ions. And this process will keep on continuing for a while until there'll be a high concentration of ions inside this lysosome. Now, this membrane of lysosome has a certain limit to how much ionic concentration it can take up. Because the ionic concentration inside lysosomes will be very high compared to the cytoplasm, water will be pumped inside the lysosome to maintain an osmotic balance. Now, since more ions are being pumped inside, more water will come inside. As a result of which, the tension in this membrane will break and that will rupture your lysosome, and your particles will be thrown out. So that's what we want. We want our particles to be delivered inside the cytoplasm and not to be ruptured inside the lysosome. So this is how we can use proton sponge effect to deliver our particles, our drug inside the cell. Now the question, let's revisit the question. The question is asking us to choose two correct options about proton sponge effect. So the correct option is particles carry secondary or tertiary amines which help in escaping endosomal and lysosomal vesicles inside the cells. And this is the phenomenon which leads to osmotic swelling and bursting of these vesicles. Am I clear in this? Did you guys get it?
Yeah,
Yes, ma'am.
Okay. Annapurna, I hope I have allowed you in the meeting. I just saw your text. It's okay, you can still join. Are you there in the meeting? Okay, thank you. Okay, so I hope I was able to explain proton sponge effect effectively and you guys have no doubts about this. If you people have any doubts, you can stop me at any point of time and we can revisit the question. So I'll move on towards the next question. Question 2 is which one is not correct about dendrimers? So dendrimers are also one type of particles we synthesize for drug delivery systems, and the question is asking us the false statement about dendrimers, and we have various options. I would like if you guys can volunteer for this question. I'll wait for a while. You can read
Ma'am, option 8.
option
Option 2, ma'am. Ma'am, 8, ma'am.
option. So I think two people are speaking. One of you said second option. They are generally not more than 100 nanometer in size. Okay, is there any other answer?
Last option, ma'am.
Okay, the last option is they're
Ma'am, last
generally
option.
okay, more than 100 nanometer in size. Okay, I have two answers. I'll wait for if anybody else wants to give it a try. So you're supposed to choose the false statement. Okay, no more answers. Okay, let's look at the right answer. So the answer is they're generally more than 100 nanometer in size is the correct answer for this. Since the question is asking us to choose the false statement. So let's look at dendrimers. Thanks both of you for answering. So, so let's see what are dendrimers. So dendrimers are these tree-like polymers which branch out from a central core and are subdivided into hierarchical branching units. So you have this polymer core and then it starts synthesizing like this, like branches. And the reason why dendrimers are used is because it's very smaller in size. So the sizes won't usually go above 15 nanometer. That is where we need to focus for this answer. And these are high molecular weight particles, very dense surface surrounding a relatively hollow core. So imagine there is this core and things start branching out from here. So your core will be very hollow compared to this surface. Your surface will have a very high density. As a result, it will have a high molecular weight. Now, how you can use these particles to deliver your drug? You can the polymers which you are using can have several functional groups such as amines, and you can modify them to incorporate your drug inside this. So since this has a hollow core, your drug can just sit in these spaces and it will be entrapped in this, and that's where you can deliver these particles. So whenever you deliver, the drug can easily diffuse out from these spaces and it will be ready to act. So if you compare the size, this is how dendrimers look like. So they are defined by their generation number. Generation meaning what? So you have this core, then the first branching out will be known as G1 generation, G0 generation, the second G2, G3, and so on. So this is how you can increase the size of the dendrimer, and that's where your drug will be encapsulated. So the question is asking us what is not correct about dendrimers. So dendrimers are not more than 100 nanometer size is the correct one. We have to choose the false option. So the false option here will be they are generally more than 100 nanometer in size, which is false. Everything else that is given out is the correct information. Is this clear? Is the question clear? Shall I move on towards the next question?
Yes, ma'am.
Okay, thank you. Okay, the next question is ranking the order of clearance of charged molecules. Pick the right one. We have to assume all particles are of the same size and below 6 nanometer. A lot of options are given. Kind of a tricky question, but if you know the concept of how particles are getting cleared from the kidney, you'll be able to answer this. I'll wait for a while. Go over the options slowly. We have plenty of time, and let me know if you guys know the answer. If not, we'll discuss.
Ma'am, option third.
Option third, which is positively charged
Option.
nanoparticles are cleared faster than negatively charged ones, followed by neutral, owing mainly to interactions with the GBM. Okay, we have one answer. Anybody else?
Option 4, ma'am.
Option 4. Okay, we have option 4 as one answer. Positively charged nanoparticles faster than neutral ones, followed by negative because of the GBM interaction. Any other answer? Thank you for volunteering. No one else wants to give a try? Okay, let's look at the answer. So the right answer is positively charged nanoparticles will be cleared faster than the neutral ones, followed by negatively charged nanoparticles, owing mainly to interactions with the GPM, which is, I guess, the fourth option. So let's look at how particles are getting cleared from kidney. So this slide I have just picked up from the lecture videos itself. So you have this GBM layer in the kidneys, and this is where your whatever you inject, nanoparticles, microparticles, any particle, any foreign particle which you inject is going to be cleared from this layer. Now if you see here, let's look at it one by one. First we'll see how based on size they are getting cleared, and then next we'll see how based on charge they are getting cleared. So you have this blood flowing here, things are going to be cleared, the blood is going to be filtered from this layer. So initially, let's say if you have a 100 nanometer size particle, that will be repelled by this endothelium itself. It will not even reach this GBM layer, which is the glomerular basement membrane. So very large particle will immediately be repelled because I think we have seen this in the first assignment also, that the size of particles. Let me take a pointer. Yeah, so this gap is only allowing particles somewhere around 10 nanometer to be filtered out. So 100 nanometer is definitely way more than that. It will immediately be repelled. Next, you have this 6 nanometer particle, which is then restricted particles more than in between these two ranges, 6 nanometer to 100 nanometer. They'll be trapped in this layer because the gap is very small for them to be cleared out. Now, if you have particles which are further smaller in size, let's say 2 to 6 nanometer, they can very readily pass through this GBM layer and they can be cleared out. Further, if you further go down below 2 nanometer, let's say you have a particle of 1 to 2 nanometer, they'll be cleared out even more faster than these 6 nanometer particles because the gap for them is very large. They can easily be filtered out from this. Now, if you go further below in the size, let's say your particle is now lesser than 1 nanometer, we'll see an inverse effect here. So I would ideally expect it to be cleared out faster, but then something else is happening here. Above this GPM, above and below this, you have this glycocalyx layer, which is made up of various sugars, polysaccharides. Now what they do is, because these particles are very small in size and this glycocalyx has kind of a branched kind of structure, so it is going to trap your particles here. So if you have particles which are less than 1 nanometer, they'll be trapped here and they'll be cleared much more lesser than what you would expect. So this is how things are getting cleared based on their size. Now let's see what happens when your particles are charged. In case of charge, all of these layers, this glycocalyx, this GBM layer, the glycocalyx below these, the GBM, everything is negatively charged in the body. Now, if you have particles that are very highly negatively charged, negative will repel and your particles will not be cleared out at a very faster rate. If your particles are very strongly negatively charged, if you have a weak negative charge, there'll be some clearance happening here. On the other hand, if you have a highly positively charged particle, they'll be attracted towards this negative charge, and if they are of a smaller size, in between 2 to 6 nanometer, they'll immediately be cleared out from this. So if your particle is positively charged, it is going to have a very high rate of clearance. On the other hand, if your particle is neutral, the clearance rate will be somewhere in between the negatively and positively charged. Now, if you see the question is asking us rank the order of clearance of charged molecules, and we have to assume everything is below 6 nanometers. So size is not going to play a role for this question. So the right answer will be, since your membrane, everything is negatively charged, your positively charged nanoparticles will be cleared out faster than the negative ones, followed by your neutral nanoparticles because of the interaction with GBM. Is this making sense? Was this question clear and the explanation followed? Let me know if anybody has doubt or if I went too fast with this. So this question just tells us that in case in your future, if you're ever designing nanoparticles to treat something and you want them to be circulating in the body for a longer time, if you make them highly positively charged, it is not going to serve the purpose. So whenever you make particles, they should be at least neutral or some amount of negative charge should be there. And positively charged particles will not be preferred. Is this clear? If no one has a doubt, can I move ahead?
Yes, ma'am.
Okay, thank you. Let's look at the next question. Which of which one of the following is correct with regard to elasticity of particles? Stiffer particles which have high modulus of elasticity can circulate for longer duration since they cannot be degraded. Low modulus particles can circulate longer as they can squeeze through tissues avoiding uptake by immune cells. If the particles are highly elastic, they can escape phagocytosis irrespective of their size, and elasticity has no role with respect to phagocytosis. So as we have already said that elasticity does play a role, I don't think so last option is a correct answer. Anybody has the right answer or any
Option
answer
two.
rather? Sorry?
Option two, ma'am.
Option 2. Okay. One answer is option 2. Anybody else? I'll wait for others. Okay, no more volunteers. Fine, we'll discuss the answer. Yes, the correct answer is, thank you for whoever answered. I'm sorry I can't see your name when I'm in the slideshow mode. The answer was correct. Low modulus particles can circulate longer as they can squeeze through tissues, avoiding uptake by immune cells. So let's look at what is happening with this clearance. So we have an organ known as spleen, which is crucial for blood filtration. So I hope you can see the screen. So let's say your blood vessel is passing through the spleen and there's this tissue surrounding this blood vessel. This is an enlarged image of the blood vessel. So let's suppose you have made particles, nanoparticles, and you have delivered it in the blood, and now they're flowing all over the body, and they cross the spleen vessel. Now, if your particle is very rigid, it will not be able to squeeze in through these gaps, and it will be cleared out from the body. On the other hand, if you have a bit of an elastic particle which can modulate its shape, you see that there are few gaps in this blood vessel. So your elastic particle can easily be squeezed from this vessel and it can go to the surrounding tissue. Again, whenever it wants, it can come back here and keep on circulating and it will not be taken up by these macrophages. As a result, it can enter this tissue. Let's say your this is the area where you want to treat this particular condition in a patient. Your particles are free to then act on this tissue, and that's where their activity mostly is centered. So they will not be cleared out from the system. So with respect to the question, which one of the following is correct with regard to elasticity of particles? So if you have low modulus particles, particles which are highly elastic, they can squeeze it from the tissues and they can avoid uptake by the immune cells. Is this making sense? So if you have highly cross-linked structures or rigid structures, even if they are of the same dimension, they will be cleared rapidly compared to your elastic particles. So it's better whenever you're manufacturing particles, it's better to have some amount of elasticity to it to avoid rapid clearance. Is the explanation clear? Did you get this? Let me know if you guys have any doubt. If not, we'll move on towards the next question. Okay. The next question is pegylation of nanoparticles is a common practice to evade uptake by phagocytic cells. Which one of the conformations of PEG is preferred to maximize this effect? Brush conformation, mushroom, orientation doesn't matter, triangle orientation, circular or cubical? Anybody wants to give it a try first? I'll wait for your response.
Option A, ma'am.
Option A is brush conformation. Okay. Any other answer? No? No more volunteers?
Option A, madam.
Okay. Thank you. Yeah, both of you are correct. The right option is brush conformation. So this is what happened. This is what the question is referring to. Let's say you have this liposome or rather any particle you have synthesized and you have conjugated it with PEG chains. Now you can have a mushroom conformation or you can have a brush conformation, but this is preferred more because since it's a brush conformation, your PEG chains are going to be flying out like this compared to this mushroom conformation. And since they are like this polymer network in nature, they are going to repel all these proteins which are trying to interact with your particle. That's what the question is asking us. Instead of your proteins, even if you have phagocytic cells here, for example, macrophages, which have a tendency to uptake any foreign material, if they come too close to this, your brush conformation PEG chains are going to repel those cells as well. As a result, your particle will be safe and it will not be uptaken. So that is what the question is asking. Pegylation is common to evade phagocytic cells. Which conformation is preferred? It's the brush conformation. Clear? Okay, then we can move on towards the next question. Sixth question is, which is the working principle behind enhanced permeation and retention effect? We have to choose two correct options. I'll give you guys some minutes to go through the options and let me know if anybody has the answer. We'll discuss EPR effect in detail. Any volunteers? It's okay, you can interact.
Option 2 and 5, ma'am.
Option 2 and 5. 2 is positive pressure between vasculature and intratumoral environment allows flow of particles from vasculature to tumor tissue. And 5 is faulty lymphatic clearance of particles from intratumoral environment. Okay, we have an answer. Anybody else? Thank you for responding. Okay, no more responses. We'll go ahead with the answer and the discussion. So yeah, you're right. Whoever answered, option 2 and 5 is the correct one. Let's see what EPR effect is. So this effect is very interesting and it has been studied more in case of cancer environment and it's still under research. So this on this slide you can see a comparison between a normal tissue and a cancer tissue. So in normal tissue, what happens is you have this blood vessel flowing, which is perfectly lined with these endothelial cells. And then you have this surrounding tissue. You have the lymphatic vessel going through this tissue. So lymphatic vessel usually plays the role of drainage. It will take up all toxic material from this tissue and it will just drain out. So in case of normal tissue, everything is perfect. If you have given your nanoparticles, until unless they are of a very small size such that they can squeeze through this gap, these will not enter the tissue. Now, in case of cancer, since you all know cancer is an uncontrolled growth, it doesn't have any organization. The cells, the tissue will be growing haphazardly, and as a result of which, in case of cancer, if you see the compare the two figures here, they have leaky vasculature. Leaky vasculature meaning they have lot more gaps in between these endothelial cells compared to your normal tissue. Because of this, now if you have given a nanoparticle, let's say below this 100 nanometer size, they can easily permeate from this blood vessel and they can enter your tissue. This is known as enhanced permeation effect. Now, what is retention? Along with having a leaky vasculature, they also have ineffective lymphatic drainage, meaning their lymphatic vessels are not that developed and they do not clear out these debris or any foreign material as effectively as the normal tissue. As a result of which, since your nanoparticles are also foreign material, they'll be entrapped in this cancer tissue and they'll not be cleared out quite easily as in the normal tissue. So that is known as the enhanced permeation and retention effect. So there are two factors playing here. One is enhanced permeation because of the leaky blood vessels. Another is your retention of these particles because of ineffective lymphatic drainage. So that's what the question is asking us. What is the working principle behind EPR effect? It is positive pressure between vasculature and intratumoral environment, which allows flow of particles from this vasculature inside the inside the tumor. And the next is faulty lymphatic clearance of particles from intratumoral environment. So both of these factors will lead to an accumulation of your nanoparticles inside this cancer tissue, which is actually what we want, because then more drug uh, will be given to this cancer tissue and it can be an effective treatment. So we're actually making use of this EPR effect. The only thing to keep in mind here is the is what size of nanoparticles you should synthesize depending upon this gap in the leaky vasculature. Is this clear? So I'll be sharing this PPT with you. You'll be getting it from the NPTEL team. So in case you guys are interested in reading more about this, I've also given the reference for this figure. You can go through this book chapter. Is this making sense? Have you got the explanation? If not, you can stop me at any time and you can ask your doubts. No questions? If not, I'll go towards the next question. So the 7 questions, which of the following methods can be used to measure size of nanoparticles? We have to choose 2 correct options. So the options are X-ray diffraction, dynamic light scattering DLS, AFM, atomic force microscopy, gene transduction, or bialistic gene gun mediated transfer. Anybody knows the answer?
Option 2 and 3.
Option 2 and 3. Okay, we have one answer. Thank you for responding. Anybody else?
Same, madam. 2 and 3.
Okay, thank you. If anyone has another answer, you can let me know. Okay, let's look at the answers. Yeah, both of you are correct. DLS and AFM are used to measure the size of the nanoparticles. If you have gone through the lectures, this is a pretty straightforward question. So, yeah, particle shape and size can be determined by 2 methods. One is qualitative, one is quantitative, and these are the methods used for that. Okay, let's look at the next question then. Which one of these is not an advantage of nano and microparticles? They're injectable, can elicit inflammatory reactions in host, possible way for delivering large hydrophilic molecules, particles can be adapted for targeted delivery, improving the stability of the drug in vivo. Any volunteers? We are supposed to choose something which is not advantageous for these particles.
Option 2, ma'am.
Option 2, okay. Thanks. Any other response? Okay, let's see. You're correct. The correct option is can elicit inflammatory reactions in host, which is not actually an advantage. So let's look at the advantages of nano and microparticles. They can act as a controlled release depot system, similar to other systems which we have already seen, such as reservoirs and hydrogels. And they decrease the non-specific delivery of the drug to non-target tissues. For example, let's say you want to give something. Suppose you have an arthritis patient, and arthritis patients are have a lot of pain in their knee. So if you want to, let's say, deliver something particularly to the knee, and instead of, so what you can do is you can encapsulate your drug in these nano or microparticles. Let's say you have PLJ microparticles and you put your drug inside that. You can directly deliver it to the knee. There is something known as intra-articular injections, which we'll see in the route of administration in the upcoming lectures. So you can directly inject your drug in the intra-articular space. This will limit the flow of this drug all over the body. Let's say if you inject something in the blood, it is going to go all over your body and it can have non-specific interactions with the rest of the organs. So that's what we can avoid by making these nano and microparticles. One of the most advantageous thing about these particles, it is injectable. You don't have to go for surgical implantation. It is a convenient way of delivering large hydrophilic molecules inside the cells, which we saw that we can use proton sponge effect for that. Particles can be adapted for targeted delivery to cells and tissues. Let's say you have this microparticles and you conjugated it with a polymer, let's say for example PEG, and on this PEG you have some, let's say an antibody, which is very very specific to if you want to, let's say, treat a patient who has cancer. Now these cancer cells will also have some antigens expressed on them, on their surface, and you have this antibody which is exactly opposite to this antigen, so your particles can quickly go to that particular site where the cancer tissue is developing. It can interact with that and your drug can be delivered. So in this way these particles can be adapted for targeted delivery. They improve the stability of the drug in vivo, because now your drug, instead of giving a free drug, your drug is inside these particles. So it will be saved from the macrophage uptake and everything. And it also improves the shelf life of the project, of the product. So in this way, these particles are advantageous. So the only thing which we don't want is it can elicit an inflammatory reaction in the host. So that's why this is the correct answer. Any doubt in this? Okay, I'll move on towards the next question then. The next question is, which one of the following parameters does not affect microparticle synthesis using double emulsion method? And these are the options displayed. So if you guys know what double emulsion method is, I think you can answer this.
Last option, ma'am.
Last is none of the above. Okay. Any other response? Okay, let's look at this. Yeah, you're correct. Thanks for answering. The correct option is none of the above. So I hope you have gone through this, but let's discuss this double emulsion process in some detail. So this is one of the methods to manufacture microparticles or nanoparticles. So first of all, what you have is, so there is also something known as single emulsion method also, which is used to incorporate hydrophobic drugs. In case your drug is hydrophilic in nature, we can use this double emulsion process. What we do in this is you have your aqueous drug solution, meaning your drug is dissolved in water phase, and it can have excipients, and this will dissolve in a polymer phase, that is PLG. For example, let's say this is PLGA and this is dissolved in an oil phase, which is hydrophobic in nature. Now, if you put your water which contains your drug inside this, and this has certain ratio, like your PLGA in oil phase is going to be much in a much higher amount compared to your aqueous drug solution. And if you stir this solution, what you're going to get is something like this. So since your PLJ is hydrophobic, it is going to trap water inside it, and inside this small blue dots, you have your drug encapsulated. Now, next what you do, you take these particles and now you're going to do the opposite thing. You're going to put this in a much higher amount of aqueous solution, which has PV. Let's say, for example, another polymer, polyvinyl alcohol, and you're again going to stir this. Now what you have is, you have this PLGA which is already hydrophobic in nature, and surrounding this you have a lot of water. So now something like this is going to happen. So this is going to break and you have water all over in bulk phase here. Then you have your PLGA here, and inside that you again have your water, and that's where your drug is encapsulated. So if you lyophilize this, if you dry these microspheres, you're going to get something like this. I don't know if you can see this clearly, but this is how the particles look like in SEM images, and you have your drug inside this. So essentially you're creating a hollow shell of PLJ inside which your drug will be encapsulated. So this is one method of making microparticles by encapsulating the drug. So the question is asking us which parameters will does not affect the microparticle synthesis. To answer this, let's first see which parameters affect the microparticle synthesis. So all of these will play an important role: the polymer type and the molecular weight of it, the polymer concentration in this oil phase, how much polymer you are putting here, Then the type of drug and the method of incorporation. If your drug is hydrophobic, it's going to be incorporated in the PLGA layer. If your drug is hydrophilic, it will be in the water phase. So both of these will affect the way your particles are made. Also, your organic solvent that is used and the polymer solubility in that organic solvent plays an important role. Also, the type and amount of surfactant in the external phase. So the surfactant is used to avoid the aggregation of these particles. Since the surface of these particles is hydrophobic, they and they are in a bulk water phase, they'll tend to aggregate towards each other, because hydrophobic will attract, and they try to move away from the water phase. So if there is no surfactant present, they'll just come together and they'll form a one big particle, which is what you don't want. So to avoid that, you add certain surfactants which will coat the surface of these particles, and they'll avoid this aggregation. So the amount of that surfactant you're putting inside this phase will also play an important role. Next, the internal aqueous phase and organic solvent ratio matters a lot. Also, the rate of stirring and the type of mechanical force you're using. For example, if you give a lot of energy during stirring, it is going to decrease your particle size. You'll have various small scale particles, and other factors such as evaporation rate, the pressure you're using, the extraction rate, everything will matter. So the only option which is right for this question is none of the above, because everything else will play an important role during your microparticle synthesis. Did you guys get the double emulsion process?
Yes, ma'am.
Thank you. Okay, we have one last question left for today's discussion. So the question is, a core shell type nanoparticle is synthesized. The radius of the core is 2 nanometer, whereas that of the whole particles is 5 nanometers. What is the ratio of the volumes of core to shell? So we give you guys some time to just grab a pen and paper and start solving. Let's see if we can get the answer. If anybody has already solved it, you can let me know.
0.064, ma'am.
0.064. Okay, we have one response. Thank you for that. Any other answer? Anyone else has solved it? Okay, let's see. Yeah, so your answer should fall in. So for all the numericals, even in your exam, you'll be given a range and your answer should fall in this range. But whoever answered 0.064 is the precise answer. So here it's a pretty straightforward question. So your core shell type nanoparticle is going to be sphere in shape. So if you know the volume of sphere, it's pretty easy. So you have given radius of the core that is 2 nanometer, and the particle is 5 nanometer. You just have to take the ratio of these volumes. So the formula for sphere volume is 4 by 3 pi r cube. You just put them together. No need to solve it separately. Just cut out the common terms, and finally you'll be 0.4. You'll arrive at 0.4 cube, which is 0.064. This is clear? You can let me know if you guys have any doubt, or if you want to discuss, if you want to revisit any particular question. Did everyone get this? Is there any question you guys want me to repeat for people who joined a little late? Also, if you guys have any doubt in the ongoing assignments or in the lectures for this week, we can discuss that as well. I'll wait for a while. Let me know.
Madam, can you repeat the question 1 to 3? I have joined little bit late.
Okay,
1
okay,
to 3.
okay. Sure, sure. Let me just share my screen again. Let me know if you can see it. Can you see the presentation? Dinesh, right? Can you see this?
Yes, ma'am.
Yeah.
I can see now.
Yeah, okay. So the first question is, what is proton sponge effect? So proton sponge effect is used when you want to deliver your drug molecule inside the cell. So what happens is, let's say this is your microparticle or a nanoparticle, and you have your drug encapsulated inside this, and you inject it in the body. Now cells have a tendency to endocytose these particles because they are foreign to the cell. So they'll take it up and they'll put it up in a endosome compartment, which will then go on to fuse with the lysosome. Inside the lysosome, the pH is very less. It's very acidic because this compartment is used to clear out foreign materials, and your enzymes present in this lysosome can chop up your particle and your drug can be degraded. So this is what we don't want. We want our drug to be in the cytoplasm. So we use something known as a proton sponge effect, which in this you design your particle in such a way that it will have secondary and tertiary amines which can sequester H plus ions, the protons. So these amines, whenever they are in an acidic environment, they'll get protonated, meaning they'll take up all H plus ions which are present inside, and they'll just adhere to this H plus ions. They'll form bonds with this. Now your H plus ions, there should be free H plus ions inside this lysosome to maintain the acidic pH of this compartment. Now, since your particles are sequestering these H plus ions, what the cell will do, it will pump more H plus ions inside lysosome to maintain the pH. Now, because of excess H plus, it will also have to pump Cl minus ions, that is chloride ions, to balance out those extra H plus ions. And this process will keep on happening because your particles will keep on taking H plus ions. Now there will be an osmotic imbalance. Your cytoplasm will have lesser ionic concentration compared to your lysosome. So water will be pumped inside to maintain this osmotic balance. Now more and more water will be pumped because your ionic concentration keeps on increasing. Now this lysosome membrane has certain limit to what amount of tension it can take, and after a while it's going to burst. So the moment it bursts, your particles can be released into the cytoplasm and your drug is ready to act. So this is the proton sponge effect, and we were supposed to choose two correct options for this. So the correct option is, in this effect, particles carry secondary or tertiary amines, which help them in escaping endosomal and lysosomal vesicles inside the cells. And this phenomenon leads to osmotic swelling and bursting of vesicles. Is this clear?
1 and 2.
Yeah, option 1 and 2.
Option 1.
Yes. And the next question was, which one is not correct about dendrimers? So dendrimers are these type of particles which have branching nature, and your dendrimers can only be about less than 100 nanometer size. So everything else about the dendrimers is correct. The only option which is not correct is they are
They
generally
are
more
generally
than,
more than.
yeah, 100
Last option.
nanometer.
Okay.
Yeah, yeah.
Third
And
question.
okay. And the third question, ranking the order of clearance of charged molecules, pick the right one. We have to assume all particles are of same size and below 6 nanometer. So this question is related to the clearance of particles from the glomerular basal membrane, which is present in the kidney. So essentially your kidneys have this membrane and your blood gets filtered through this. So we are supposed to assume that the size is same. So if your particles are of size 2 to 6 nanometer, they can easily be cleared out from this membrane. So in the question, we have to assume that all particles are below 6 nanometer and we just have to see the charge. Now, depending on your charge, the clearance rate of these particles will change because your GBM, this membrane, and the glycocalyx membrane surrounding this GBM is negatively charged in your body. If your particles are highly positively charged, they'll be cleared out very quickly because of the positive negative interaction here compared to the neutral particles. And if your particles have highly negative charge, they'll be repelled by this system, by this negative charge of GBM layer and glycocalyx layer, and they'll not be cleared out as easily as the positively charged ones. So we, in the question, we are supposed to rank them in this order. So the correct answer is your positively charged nanoparticles are cleared faster than the neutral ones. Then they'll be followed by the negatively charged particles because of the interaction with the GBM. Did you get this?
Option 3.
I think this is, yeah, I think this is option 4. If you see
Option
the,
4.
yeah, because positively will be cleared out faster than the neutral and then the negatively charged.
Positive
Yeah,
charged.
yeah, this positively will be cleared out first, then the neutral and then the negative ones. So that
Okay,
will be
madam.
the order.
Okay, madam. Thank you.
Yeah, thank you. Anybody
Can you
else has a
discuss
doubt?
about the other remaining questions?
Sorry.
Fourth, fourth to ninth questions.
Oh, you joined late, is it?
Yeah, I'll join.
Okay, okay, sure. I'll go over it quickly. Yeah, okay. So the fourth question was, which one of the following is correct with regard to elasticity of the particles? And the option was, the answer was low modulus particles can circulate longer because they squeeze through the tissues, avoiding uptake by immune cells. So if you see this structure of how things are getting cleared, blood is getting filtered from spleen. If your particles are very rigid, they'll immediately be cleared out. On the other hand, if you have elastic particles, they can easily squeeze through this structure from the spleen and they can avoid uptake by immune cells. Is it okay?
Yeah, okay.
Yeah. Next was pegylation of nanoparticles is a common practice to evade uptake by phagocytic cells, and we have to choose which conformation of peg is preferred to maximize this effect. So the answer was brush conformation. So you can conjugate peg to your particles. Let's suppose your liposome is the particle, and you have conjugated peg in two different conformations. It can either be a mushroom where it just collapses along with the towards the surface. Compared to that, if you have a brush conformation, it will just be peg chains lying around like this, and we have to select which one will be better. So obviously this brush conformation is better because it then avoids protein and cell interaction. If suppose a macrophage or any other cell is coming closer to your particle, they can easily repel it and avoid uptake by the phagocytosis process. So that's the
Okay.
that was the question, which is better. So the brush conformation is better than the mushroom.
Okay.
Next was, which is the working principle behind enhanced permeation and retention effect? So EPR effect is most prominent in a cancer tissue, where if you see this diagram, this is a comparison between normal and tumor tissue. So in tumor tissue, what happens is your endothelial cell, which is the lining of the blood vessel, is leaky in nature. it has more gaps compared to your normal tissue. And if you inject your nanoparticles in the body, they are going to flow in this bloodstream. And because the gap here is now larger, they can easily permeate from the blood vessel in the cancer tissue. So this is the enhanced permeation effect. Now what is retention is along with, so because this cancer tissue has a very haphazard orientation, the lymphatic drainage that happens in a normal tissue, it is not as well developed in the cancer tissue. So your lymphatic system will not be able to clear out the debris or the foreign particles which is present here. So as a result of this, it will not be able to clear out your nanoparticles also. So this is the enhanced retention effect. So both of these effects put together, enhanced permeation and retention, is actually beneficial when you're delivering drugs to the cancer tissue. So the principle behind it is positive pressure between your vasculature, that is your blood vessels, and intratumoral environment allows flow of particles from vasculature to tumor tissue. And faulty lymphatic clearance of particles from intratumoral environment will retain those particles inside. So that's the EPR effect.
Okay.
Okay. Next was, which of the following methods can be used to measure size of nanoparticles? This was pretty straightforward. There is DLS, that is dynamic light scattering, and AFM, atomic force microscopy. Both of these are used to measure the size. Then eighth question was, which one of these is not an advantage of nano and microparticles? So your first, let's see the advantages of it. Since nano and microparticles can be injected, you don't need surgical implantation. You can just take it up in a syringe because they're smaller in size and inject in the body. They are used for delivering large hydrophilic molecules inside the cells. They can be adapted for targeted drug delivery, and they can improve the stability of drug in vivo. The only option which we do, the only disadvantage of these systems is they can elicit inflammatory reactions in the host. So that was the question. Is this clear? Are you still there?
Yeah, I'm there.
Yeah. Okay, and the ninth question was, which one of the following parameters does not affect microparticle synthesis using double emulsion method? So this is the double emulsion method where you have your aqueous drug. So double emulsion method is used to incorporate hydrophilic drugs inside microparticles. So you have your drug dissolved in an aqueous solution, water base, and you have your polymer, that is PLJ, which is a little hydrophobic in nature, that is dissolved in your oil phase. Now, if you stir this mixture at a giving it a very high energy, you will get something like this. You will have your PLJ and you will have water droplets trapped inside this PLJ. That is where your drug is going to be. Now, if you further put this particle in an bulk aqueous phase and again stir it, you will get something like this. So the bulk of this, the white thing here is your water phase. You will have a PLJ particle which will form a hollow sphere, and inside that you will have water, and that's where your drug will be trapped. So the question is asking us, in this entire process, what are the parameters which will not affect the particle synthesis? So definitely your polymer type and molecular weight is going to affect the concentration in oil phase, what organic solvent you are using and how your polymer is going to be soluble in that is going to matter. So the amount of surfactant you put in the external phase here, because surfactant will avoid the, so since both of these particles are hydrophobic in nature, your PLGA on the surface is hydrophobic, they can come together and form a big particle, they'll aggregate. So you use surfactants to avoid that aggregation. So the amount of surfactant you are putting will also change the size of your microparticles. Also, the other factors like internal aqueous phase to organic solvent ratio and how much mechanical force you're giving during the stirring is also going to matter. So the right answer for this question was none of the above, meaning all of these parameters will affect your microparticle synthesis. And then last was I think you were there for this question.
Yeah,
So
I was there.
yeah, so this is just a straightforward formula.
Okay, ma'am. Thank you. Thanks a lot.
Yeah, welcome. Anybody else has a doubt? If no, then we can stop the meeting here.
No,
And
thank you, ma'am.
yeah, most welcome. We'll meet next week with fifth week assignment. Okay, thank you all. Bye bye.